Welcome to Defenders, the teaching class of Dr. William Lane Craig. Today, The Existence of God, Part 14. And for more information and resources, go to reasonablefaith.org.
Well, we've been talking in class about arguments for God's existence, and we have a new outline for the next section on the teleological argument. Oh, the argument map. Okay, let's first distribute the argument map for the Kalam cosmological argument, which we have just finished. And then we should also have an outline for the teleological argument, which is the argument to be discussed. Now, while those outlines are being distributed, let's take a step back and reconnoiter and get the big picture of where we are. We began our survey of Christian doctrine with the doctrine of revelation. And then we moved to the doctrine of God. And we first had a lengthy examination of the attributes of God, in which we talked about what God is like. Then we began a section on what's called natural theology, which explores what we can know about the existence and nature of God apart from divine revelation in Scripture, through human reflection, human reason alone. And in our excursus on natural theology that we have been embarked upon, we first looked at the contingency argument for God's existence that Gottfried Wilhelm Leibniz defended. And then after the contingency argument, we looked at the Kalam cosmological argument, which has a rich Jewish and Muslim history as well as Christian background. And having now completed the Kalam argument, we're ready to turn to our new argument, which is the teleological argument. And this comes from the Greek word telos, which means purpose or end or goal. And this is the famous argument for design. It's an argument for a cosmic designer of the world. This is one of the oldest arguments for God's existence. The ancient Greek philosophers, Plato and Aristotle, each defended versions of the teleological argument. According to Plato, there are two things that lead people to believe in God. The argument from the existence of the soul, which we haven't looked at, and then he said the argument from the order of the motion of the stars and of all things under the dominion of the mind which ordered the universe. The order of the motion of the stars and of all things under the dominion of the mind which ordered the universe. And Plato referred to this mind that orders the cosmos as the maker and father of all, the king who is the source of the rational cosmos in which we live. His pupil Aristotle has an even more splendid statement of the argument for design. Aristotle imagined what it would be like if there were a race of men who lived underground all their lives in a cave, and who suddenly, through an earthquake or something, managed to escape and come out and see the external world. And this is how Aristotle describes the impact that seeing the world would have upon these men. He says, when thus they would suddenly gain sight of the earth, seas, and the sky, when they should come to know the grandeur of the clouds and the might of the winds, when they should behold the sun and should learn its grandeur and beauty, as well as its power to cause the day by shedding light over the sky. And again, when the night had darkened the lands, and they should behold the whole of the sky, spangled and adorned with stars, and when they should see the changing lights of the moon as it waxes and wanes, and the risings and settings of all these celestial bodies, their courses fixed and changeless throughout all eternity, when they should behold all these things, most certainly they would have judged both that there exist gods and that all these marvelous works are the handiwork of the gods. In his book, The Metaphysics, Aristotle goes on to argue that there must be one first uncaused cause, a prime mover, a first uncaused cause, which he refers to as God, a living, intelligent, immaterial, eternal, and most good being who is the source of order in the cosmos. And as you read the works of these ancient Greek philosophers like Plato and Aristotle, you cannot help but think of Paul's letter to the church in Rome, where in chapter 1 and verse 19, he says, "Ever since the creation of the world, God's invisible nature, namely his eternal power and deity, has been clearly perceived in the things that have been made." From the earliest times, men who are totally ignorant of biblical revelation have looked at the order and beauty in nature and inferred that there must be a designer and God who has created the universe. And today, many astronomers are coming to a similar conclusion. Scientists used to think that whatever the initial conditions of the universe might have been, eventually, given enough time and some luck, that intelligent creatures like us would evolve somewhere in the cosmos. But in fact, as a result of discoveries over the last 40 or 50 years, what has happened is that we now know that that assumption was wrong. In fact, the exact opposite turns out to be true. What astronomers have discovered is that the initial conditions of the universe in the Big Bang had to be finely tuned to a precision and delicacy that literally defies human comprehension if intelligent life forms are to evolve anywhere in the cosmos. And this delicate balance of initial conditions present in the Big Bang has come to be known as the fine tuning of the universe. From its earliest inception, the universe appears to be fine-tuned for the existence of intelligent life with a precision and delicacy that are literally incomprehensible. Now, there are two kinds of fine-tuning. The first involves what are called the constants of nature, and the second involves certain arbitrary quantities that characterize the universe. So let me say a word about each of these. First, the constants of nature. What is a constant? Well, when the laws of nature are expressed as mathematical equations, you find appearing in them certain symbols which stand for unchanging quantities. For example, the force of gravity, the gravitational constant, or the electromagnetic force, or the subatomic weak force. So, for example, take Newton's gravitational law, that to calculate gravitational force, you take the gravitational constant g, and you multiply this by the masses of the two bodies that are attracting each other. If you have two masses, say 1 and 2, to figure out the gravitational force between them, you take the gravitational constant times the mass of these two objects divided by the distance between them squared, which we can symbolize as r. And of course, the masses of the objects may vary. They may be two planets, they may be two billiard balls, they may be a billiard ball and a planet. Those can vary. The distance obviously varies depending on how far apart the objects are. But g is a constant. It always has the same value. And the values of these constants are not determined by the laws of nature. There could be universes that are governed by exactly the same law. You could have the same force law, but g could take some other value. The value of g is independent of the law of nature in which it occurs. G could have any of a wide range of values, and the law would still be the same. And you would have a different kind of universe, obviously, if you changed the value of g. So you could have universes which are governed by the same law, but have different values of the constants. And these universes would look very different from our universe. So the actual value that g has is not determined by the laws of nature. It's independent of the laws of nature. And depending on what value these constants take, the universe will look very different. Now, in addition to these constants, there are also these arbitrary quantities that are just put in as initial conditions on which the laws of nature operate. You have certain initial conditions, and then you apply the laws of nature to them to predict certain outcomes. And because these quantities are arbitrary, they're also not determined by the laws of nature. You could have different initial conditions, and then the laws of nature would predict different outcomes. So, for example, one quantity would be the amount of thermodynamic disorder or entropy in the early universe. You remember when we talked about the second law of thermodynamics, we talked about how it predicts that entropy will increase over time as things become more and more disordered thermodynamically. The amount of entropy is just put in the Big Bang as an initial condition. And then the laws of nature take over and determine how things will develop from there. And if the initial quantities had been different, then the universe again would look very different today. It would predict the evolution of a quite different universe if you alter the initial conditions. Now, as I say initially, and for a long time, scientists thought it doesn't really matter what the initial conditions and constants were. They could take a wide range of values and things still might evolve to produce complex life forms. Instead, what they have been stunned to discover is that these constants and quantities must all fall into an extraordinarily narrow range of life-permitting values in order for complex life forms to evolve and exist anywhere in the universe. And this is what is meant by the term the fine-tuning of the universe. It refers to the fact that these constants and quantities have to fall into this very narrow range of life-permitting values if life is to exist. So, it's important to understand that the term fine-tuning does not mean designed. It does not mean designed. Otherwise, the argument from fine-tuning would be question-begging. If you said, well, the universe is fine-tuned for our existence, well, then it means it's designed for our existence. No, design is one of the explanations of fine-tuning. But fine-tuning doesn't mean designed. It's meant to be a neutral term. Fine-tuning just means that the range of life-permitting values of these constants and quantities is exquisitely narrow. If the values of these constants and quantities were to be altered by even less than a hair's breadth, the life-permitting balance would be destroyed and the universe would be life-prohibiting instead of life-permitting. Any question there, then, about the definition of fine-tuning? Tom, over here, Steve. Tom.
So it sounds like it's safe to say that fine-tuning is a fact. I mean, the universe is fine-tuned, and is it universally accepted that that means that the life-permitting part of it is also sort of unquestioned?
Yes, I think that this is really uncontroversial among those who understand the term. I'll say something more about this and give some examples of fine-tuning. But as a neutral term that is not a synonym for designed, fine-tuning is just a fact. It's just a scientific fact that the constants and quantities have to fall into this very, very narrow range or the universe wouldn't be life-permitting. Yes, David.
It's a little hard to ponder how fine-tuning of the constants and the arbitrary quantities can be embedded in a singularity. For example, it's a little hard to imagine how a singularity could have any entropy at all. Have astrophysicists gotten very far in figuring out how this works?
No. In fact, what we're talking about here, when I talk about the early universe, I don't mean the singularity. Some of these constants and quantities result from quantum phase transitions that the universe goes through very, very early. You have first this unified theory, some sort of a quantum theory of gravity, in which there aren't separate gravitational particles or electromagnetic forces and so forth. You just have a unified force. Then you have this so-called gut era, where you have a grand unified theory where you have gravity break loose from the other three fundamental forces of nature, and that will then involve this fine-tuned gravitational constant. And then you have it break down further into the fundamental forces of nature, like gravitation, electromagnetism, the weak force, and the strong force. And as the universe goes through these quantum phase transitions, what happens is these finely tuned values just fall out one after another, inexplicably, because these are supposed to be indeterminate phase transitions. So when I said from the beginning, I didn't mean from the singularity. I mean from the very, very, very early universe. But in fact, they do fall out serially as the universe goes through these phase transitions. Yes, Bob?
I'm having a hard time understanding why the differences between fine-tuning and design are qualitative rather than just quantitative. Why couldn't you just say, well, this is just a finer, it's just putting a fine point, but it's still design? Didn't these constants and these quantities have to be part of a design also?
I think that we'll see that these aren't synonymous terms at all, Bob, that this isn't just a quantitative difference, but rather there are other explanations for the fine-tuning. For example, chance would be one, the many worlds hypothesis. There are parallel universes where the constants and quantities take every possible value in some universe. Or some people will try to bite the bullet and say it's physically necessary that the universe exists with these values of the constants and quantities. So there are other explanations of the fine-tuning than design, which underlines the fact that it isn't synonymous with design. Design will be one explanation of the fact that in order for life to evolve and exist in the cosmos, these constants and quantities all have to fall within this very, very narrow range. Yes, over here. And remind me of your name again? Bruce. Okay, let's get it on the mic here, Bruce.
Wouldn't the fact that you can represent these qualities and constants mathematically be an evidence for design? The ability to mathematically represent would
I don't think that simply the ability to represent them mathematically requires design. So, for example, take this constant g. Suppose you could show that g could take any of a very wide range of values and life would still exist. Well, then that wouldn't really be finely tuned in that case. So it's not just that it can be represented mathematically, but it's the precision of these values for life that is really at issue here. Okay, any other comment or question? Yes, Tom. Oh, I'm sorry, Joe first, okay.
I'm reminded of Victor Stanger's argument about this not being very imaginative, that we're just dealing with things that we can observe in our real small local area of a vast social system. We need to be more imaginative and think maybe the constants are completely different elsewhere, maybe not even in another universe, but in the one we inhabit. So what would you say to that?
These constants and quantities, Joe, as I said in response to David, characterize the early universe so that these are cosmic values. These are not local to our galaxy or the Earth or our galactic cluster. These are cosmic conditions. So this completely evacuates of any force and appeal to the size of the universe as an explanation for how life could exist somewhere by chance. These are cosmic conditions that must be present for life to evolve and exist anywhere in the universe. The only way to get around that would be to posit other universes. Now, we'll talk about that later on. That's the so-called world ensemble hypothesis or multiverse hypothesis. But when you're just talking about the size of the universe, this argument circumvents that because we're talking here about cosmic initial conditions. Yes, Tom.
I notice you say it's necessary for life. You don't say necessary for life as we know it. Are there other forms of life that
I'll
could
address
exist?
that question in a minute. And you're correct, Tom. You're very perceptive to see that. I think that when you say life as we know it, people think, oh, well, then if the constants and quantities being different, little green men with pointy ears might have evolved, or slime molds or something of that sort. And that would be totally misleading. It's life that wouldn't exist in this universe if the constants and quantities were different. As we'll see, if these constants and quantities are altered even a little, what happens is you wouldn't even have chemistry. You wouldn't even have matter, much less planets and stars that could serve as places where life might evolve. So that kind of response simply doesn't understand the catastrophic consequences of altering these constants and quantities. And I'll say something more about that later on.
And so is life defined as sort of like some living, breathing, biological
right.
form?
Again, I'll
is
say
that
something
right?
more about that in a little bit. But by life, scientists simply mean something like this: the ability of an organism to take in energy, metabolize it, and reproduce after its own kind. And anything that can do that is called life. So it doesn't have to be anything of a form familiar to us. It just has to fill that very generic definition of being able to do something of that sort. And your name is? Jonathan, okay.
I was just curious if this particular issue is specific to one particular cosmogony, or is it something that basically any cosmogony model needs to address?
It's one that any cosmological model needs to address. These finely tuned conditions are independent of whether you're talking about a standard Big Bang model or an inflationary model of the universe or some ekpyrotic model or even a steady state model. These conditions are conditions that are necessary for life to exist in the universe. All right? Well, let me give some examples of fine-tuning, because physics abounds with examples of fine-tuning. But before I do so, let me give you some numbers to give you a feel for the delicacy of the fine-tuning, because otherwise the numbers are just so large they become meaningless to us. The number of seconds in the history of the universe, from the very beginning of the universe, is about 10 to the 17th power. Now that's 1 followed by 17 zeros. Just an incomprehensible number. That's the number of seconds in the history of the universe. The number of subatomic particles in the entire known universe is around 10 to the 80th power. Now, with those numbers in mind, consider the following. The atomic weak force, which operates within the nucleus of the atom, is so finely tuned that an alteration of even 1 part out of 10 to the 100th power would have rendered the universe life prohibiting. In order to permit life, the weak force has to be fine-tuned to 1 part out of 10 to the 100th power. Similarly, the so-called cosmological constant, which drives the acceleration of the universe, has to be fine-tuned to with 1 part out of 10 to the 120th power in order for the universe to be life-permitting. Here's a real corker. Roger Penrose of Oxford University has estimated that the initial entropy condition, the entropy level of the early universe, has to be fine-tuned to 1 part out of 10 to the power of 10 to the power of 123. A number which is so incomprehensible that to call it astronomical would be a wild understatement. And it's not just one of these numbers that must be fine-tuned, but all of them, so that you multiply these probabilities together until our minds are just reeling in incomprehensible numbers. Having an accuracy of even 1 part out of 10 to the 60th power, 1 part out of 10 to the 60th power, would be like having a range the size of the entire visible universe, 20 billion light years across. And in order for life to exist, a randomly thrown ball, say, would have to land in an area 1 inch in length. So imagine a 20 billion light year distance. In order for life to exist, just a randomly thrown ball would have to land within this specific 1 inch square. And that's just 1 out of 10 to the 60th. And we're talking about numbers that are just unimaginably greater than that. And this is just some of the examples of fine-tuning. The examples of fine-tuning are so many and so various that they're unlikely to disappear with the further advance of science. Like it or not, the fine-tuning of the universe for life is just a scientific fact, which is well established. Any comment or question on any of those examples? Yes, Don Pendley.
My question is this. At what number does it cease to be a probability and become a certainty? And what is that number?
That is a very, very interesting question, Don, actually. When do probabilities become so great that you say this is now an impossibility? It is meaningless to talk about 1 chance out of 10 to the 10 to the 123. Well, William Dembski is an expert in mathematics and probability theory, and he wrote a book called The Design Inference, in which he raises this question to try to determine what is a reasonable probability bound. And Dembski takes this number, 1 chance out of 10 to the 80th power, to be the probability bound beyond which things are impossible. Anything that has a probability that is less than 1 out of 10 to the 80th power becomes impossible and will never happen. So that's the bound that Dembski adopts, at least in that book, as his probability bound for the difference between what becomes impossible and what is probable or improbable. Any other comment? Yes, Jonathan here again.
How exactly is that value determined? I mean, it seems almost like it's an arbitrary selection.
Well, I think that the reason, well, it wasn't arbitrary. The reason that Dembski picked it is precisely because it is the number of all of the subatomic particles in the universe, so that you couldn't have any more events, in a sense, than that. And therefore, anything that exceeds that, in terms of its improbability, is impossible. So he bases it on the number of particles in the universe. Yes, Steve. You're asking, is the strong force fine-tuned? I don't recall seeing anything in the literature about the strong force. Not all of these constants and quantities are fine-tuned to the same exquisite degree. Some of them have a greater range. For example, gravity doesn't need to be as finely tuned as the weak force. You could alter the gravitational constant somewhat and still have life. But after a while, it would get too heavy and animals would collapse because they couldn't sustain themselves. Their bodies would collapse if gravity gets too heavy. If gravity gets too weak, then matter would never coagulate together into planets, and everything would just drift apart. So gravity also has to have a finely tuned range, but it's not nearly as exquisitely narrow as some of these others. And I don't remember, Steve, where the strong force falls. You might take a look at a book on this question like Barrow and Tipler's book, The Anthropic Cosmological Principle, where they discuss these various fundamental forces of physics. But I don't think that the strong force is one that is used as a typical illustration of an exquisitely finely tuned constant. Any other question? Yeah, Joe. They do talk about that. Barrow and Tipler's book, The Anthropic Cosmological Principle, is primarily a discussion of these constants and quantities. But they also have sections in which they look, for example, at the nature of water and the extraordinary properties that water has that enable the universe to be life-permitting. And they do talk a little bit about those, but not to the same degree that they talk about the constants of physics. People who are proponents of the teleological argument will often go beyond the fine-tuning of the cosmos to talk about how special the Earth is as well. You need to have a moon, for example, to create tides. You need to have a Jupiter in your solar system to act as a kind of vacuum cleaner that will pull away meteors, asteroids, and comets to keep them from pummeling your planet and destroying it. You need to be a certain distance from the star in order to have the right heat that permits life without incinerating it or making it too cold. There are any number of those sorts of things as well. But this argument from fine-tuning alone just does an end run around all of that and goes right back to the very initial conditions. If this argument works, then all of those other things will simply layer on more improbability and more evidence for design. All right, well, what we'll do next time is to look at the objection that if the constants and quantities had been changed somewhat, then maybe different forms of life would have evolved, which Tom raised, and we'll also then talk about the objection that maybe there could be a universe governed by different laws of nature, and those might be life-permitting. So next Sunday, we'll move into a further discussion of objections to this argument as it stands so far.
The copyright for the content of this recording is held by Dr. William Lane Craig. For more, go to reasonablefaith.org.